hi everyone. So welcome to this lab session, and we had seen that how we can install all the Vivado, Vitis HLS, all the different things, and also you can double click for here to start, or you can simply wherever you've installed, maybe it's in your slash tools. Some of you like in IPC might be using slash tools. I have installed it at my home folder, so for me it will be the home folder, and here I can see Vivado, Vitis, all these things. So I can go inside any Vivado, and here you will see a settings.64sh script. So if I print this script, then what it is doing, it is internally sourcing many other scripts, and that will be the thing in everything, like it is sourcing all these scripts together. So I can just type source dot slash setting64.sh, and now it has internally sourced these different files, and I can simply call Vivado software from here as well. So this is how you simply can launch Vivado, Vitis, and it will keep on showing what you're doing in the GUI as a command line option. So it states start GUI, and then you will see this option load up. So in Vivado, I'm guessing that you already have an experience of opening the Vivado software. So in this lab session, first of all, get an experience on the GUI, Vivado and Vitis. So this is how the Vivado software looks like, and in here I can click on create project, and you can see that this is the first option, might not be visible on the screen, so okay. You can click on create project, and you can start to create a project. You can simply choose a folder where you want to create the project. It's showing the project location as inside the main installation folder, which is not recommended to do it in the installation folder, but just for the sake of showing, let's go ahead with that. Since we don't have any sources right now, we do not specify sources at that time, so it's an RTL project which we can create. It's a post synthesis project. Like the synthesis step is already done, then IO planning, imported project, example project. So all these things are there. Then you can choose the different boards on which you can just choose different boards which you have. So we have ZC104 in this. We have certain older boards. So on searching, you can see that there are 3-4 variants of Kriya, which is Kriya KV260, Kriya KR260. So we can choose this board. Here we can see the different information about the board, like the IO pin count and the available IOBs, LUT elements which are present. So you see that Kriya KV and KR are almost similar because they are using the same chip, but the dev board is different. The development board, the interfacing, that is different. Broadly, the IC is the same only, the IC which we are using. So you can click on next, and you can click on finish project. So it's of the family of Zinc MPSOC series, and so it has initialized the project. On the left side, you see the project manager, and you might have done the standard scheme of creating an IP, or creating the design sources, adding the RTL files, the Verilog files. But the way which we will choose actually, so you can see that there is this IP catalog as well, in which there are already so many IPs which you can directly use for your FPGA. Some of the interesting one being the cryptography libraries for doing the advanced encryption, AES, and for each IP which you are seeing, you can see that it has for every IP there is a documentation available. So it talks about the product description that AES core provides encryption and decryption functions that are compliant to the FIPS publication. The core comes with built-in key expansions for both encryption and decryption functions, and enables customer to accelerate data center storage, NVMe encryption decryption, by offloading this critical processing of data at the full line rate, 100 Gbps. So there are certain key features and benefits which it offers, that there is EXI stream interface with 128, 256 and 512 data width options, and it supports these sorts of encryption schemes. And supported device family includes the Zinc Ultrascale RF SOC, Kintex Ultrascale, Zinc Ultrascale MP SOC. So all these things you can read about it, and for for more information you can actually refer to this IP product guide. So that's how these all things are structured in a very standardized way. You can read about it as per your functionality. For digital signal processing, there are many filters which you can see, like FIR filter, CIC filter for modulation techniques, transforms, DFT, fast Fourier transforms, so some trigonometric functions, waveform synthesis, all these things you can see that these IPs can directly be used, and they are EXI4 stream. Most of you will see are EXI4 stream enabled, and yes, moreover you can create your own IPs and can package it and can sell it even. So there are certain math functions available with us, like dividers, floating points, multipliers, and all these will get actually, rather than writing the Verilog code for doing all these things, you can just import these IPs in your program. For video and image processing, we have EXI4 stream to video out, so EXI video direct memory access. So with DMA you can actually store it into the DDR memory, can get the video from there, and certain filters, processing subsystems, and connectivity ports are also there. So in order to use all these, we generally do a create block design, and it's creating the block design right now. So this is, we're calling as design 1, and a very standard, for the platform setup, like how the board is performing, how the board is working. So you can click on add IP, and the first IP which we would generally add, because we want the PSPL connection together, would be the Zinc. Is there an option to search? Okay. Would be the Zinc Ultrascale MP SOC. So this is the IP for actually processing your PS and the PL configuration, and you can see that it has opened up the whole board view, with majority of it being the PS side of things. Now PS looks big when you're doing it this way, and PL, which you can see here, looks small, if you can follow my mouse pointer. But in actually, PL is much bigger than PS, and PS occupies a small portion on the fabric. So you can choose to actually click on any place, and you can configure those things, that how the DDR configuration is. So enable DDR controller, and memory type DDR, DDR3, what type of memory you are wanting to actually interface. Then there are different options. So most of these things you do not change unless you have a very specific use case. You just let it remain as it is, and let the software itself do things, because all these things are very too low level details for us to actually work on certain applications, and we don't go to that low level. Regarding the PSPL configuration, so you'll see that there are certain interrupts which you can raise from PL to PS. So those interrupts will start coming also, like if I just, let's say, if I enable certain configuration, so you can click on select, and if you select all these things and you press on OK, so you'll see that the ports for them have started to appear. So depending on which all things you require in your design, you actually enable, disable those things. As a standard scheme as of now, so PSPL master interfaces, you can enable full power domain, like high performance, in EXI high performance ports. You can enable different things, master interfaces, slave interfaces, and to understand all these things we've covered quite in detail in the theory lectures, so I would encourage you to watch those lectures. As of now, I'm disabling all of this, and even for clock configuration, we'll let it remain to standard. You can switch to some advanced mode where you can actually do the PCI configuration, but we, as I said, we do not do all these configurations manually. we can simply run on block automation and it will apply some board preset to it. With the board preset, it gives access to standard set of interfaces, and like it will enable the FPD, like some interrupt requests and certain full power domains clocks it will enable. So that's how it will do. You can actually click on add IP and select another IP, let's say GPIO, AXI based GPIO which you want. Let me expand this view if possible. Alright, so you can click on run connection automation and you can choose that which all GPIO and slave AXI will connect to which master. So if it's slave AXI port on the GPIO, it will get connected to a master AXI port on the PS. So here the PS will be the driving factor. So on connecting all this, again we can click on all automation. So it's doing the reset connection on the external reset pin and doing the master AXI HP1 connection. So all these connections now we can choose to actually regenerate the layout in order for it to look better. So we can map these GPIO RTL, this port we can map to some custom thing in our maybe a push button somewhere where we can reset this processor system completely. And this is utilizing the Zinc architecture in background. And since we are actually trying to connect a GPIO, since we're trying to connect a GPIO which is AXI enabled GPIO to our PS via the AXI port, so therefore we require an AXI interconnect in between, so which it has automatically configured for us. So now if we have to access the GPIO pins from the PS side, then how it will work is that you go to your address editor and you can see that the AXI GPU pins, so this is GPIO pins. So the slave segment is register and the base address is in hexa it is 8000000 and the range is 64K. So you can change the range based on how much range you want, and definitely based on the range which you select, the master high address will be selected. You can go to address map and you can see that this is how this, if you in the AXI protocol, if you will refer to these addresses, then it will get mapped to the GPIO pins, the GPIO register, sorry. So let's actually try to verify the design now. So you can click on validate design and we'll say the validation design is successful. There will be some warnings which might be coming, but we can ignore those warnings. You can click on create validate design, we've already clicked on. So next you can go and click on inside the source folder. You can come here. So all the we are generally used to Verilog files like .v files. So this is known as an IP integrator tool. So you can just integrate your IP. You can just integrate your IP inside this, and the file name would be called BD file. So it's like a block design file, and you can click on this, and here you can click on create HDL wrapper and let Vivado manage wrapper and auto update. So it will just create a Verilog file for you, and inside this Verilog file it will import all these ports and everything, like whatever you would have written the code for. Inside that it has automatically created a wrapper, so it has imported all these IPs for you and created a design for you. So the design is right here, and then you can check the configuration, like how the design files are made. Obviously at very low level, these IPs you cannot access the code of these IPs, you can just see the port as they are AXI enabled. So all these things are automatically coming up. So you don't have to worry in order to make things AXI enabled. It's like industry standard thing which you can directly use in production. And you can see the different so it's a you can see the different parts of the code here. So just like I'm just showing it to you for exploration, that inside it's still the Verilog code which is being converted to RTL. Now what we'll do is, once we have this design wrapper with us, we will refresh, update, set library. Alright, so once we have the design with us, we can actually it's giving the option, we can follow this flow, we can run a simulation on this, we can run linter, run synthesis, run implementation, and can generate the bitstream and can program the FPGA directly. So besides the linter was taking time, so we have completed the synthesis and the implementation step. So you can now click on generate bitstream and can program your FPGA, or you can just click on open implemented design and can see like what all things like what does implementation step really mean. So in synthesis we actually convert the high level design which you've written either by importing the board design or using the Verilog or VHDL into gate level netlist, and the synthesis process optimizes and maps the HDL code to basic logic elements such as the LUTs, the flip-flops, and the other primitives which you are there specific to the FPGA architecture which you are using for it to implement on. And this you can see in the project manager itself, that once you have you can click on project summary, and after implementation like post synthesis you can see that how many in table form that what resource it was taking, and post implementation how much LUT RAM flip flop it has taken. So along with some estimation of the power and some timing diagrams, certain timings like it has calculated, and yes, basically this. In implementation, when synthesis is complete, so by the end of synthesis the design is technologically mapped but not yet placed and routed on the physical FPGA. In the implementation step, the placement, routing, and the timing analysis takes place, and it is actually responsible for translating the netlist into a physical layout of your FPGA. So now depending on which FPGA board you have chosen, so in the previous step also it was board aware, like in the dashboard, so not in the dashboard, in the overview itself, like we have the project part coming, and based on that only the synthesis, like how many resources it has to map to, whether it can be mapped to those many resources or not. After that implementation, the placement, routing, and timing analysis takes place. In placement, we assign the logic elements from the netlist to the specific locations on the FPGA. So if I show you in the practically where we are seeing that, so in open implemented design we can go to schematic, no, not schematic actually, yes, right here in the device itself you can see that how it has implemented the different logics in different parts of the FPGAs. You can keep scrolling and like in the most fundamental layer you will see the LUT implementation and the flip-flops which are there, the BRAMs which are there, what all it is using, that is highlighted all in blue, and even in this DSP slices, what all slices or GPIO pins it is mapped to, that also is indicated. And this thing here being your PS, that how the PS is actually mapped, nothing which you can view here. And obviously you have different type of schematic diagrams which show you that how the design GPIOs RTL, how the ports are flowing, so you can check definitely the schematic, and also you can see the data flow design. This shows that how the data is flowing in different parts, like what all ports are mapped to which ports. And finally you can click on generate bitstream. So this is for any application Now, what we'll do is we'll do a very specific application of the resizer IP which we did in lab 3. We'll try to generate the block design using Vitis, like using Vivado and Vitis HLS for that. So I'll click on open terminal and we'll clone this repository. The pink repository here. So this is the pink hello world example which we saw and explored in we'll go to the original repository itself. This was one of the examples which we had seen in lab 3, and inside we had seen two notebooks which were there. In the notebooks for the edge we saw that there was the resizer PL and the resizer PS. The resizer PL notebook actually uses this resizer.bit file and the hardware handoff file. So this is the link for that, and it actually downloads these hardware handoff files, and so you can just download it for different boards like for KB260 and everything. You can just download it, or including the bit file, or you can actually generate it. So this is the bitstream file, and that is the hardware handoff file, HWH file. So we'll in this lab we'll generate these two files. So for that we'll just clone this repository first, code, and we'll do git clone this repository. So we can open this repository, we can cd into this pink hello world and can explore this file. What we'll do along with this is open this in the code. So code -n dot. This will open the whole thing in the VS code, and here we can go to the boards and we can see that in the IPs folder, in the source folder, it has references to certain HLS code and the resize accelerator, the resolution conversion. So like it has linked everything. So let me just first of all give you a quick view of what all this repo contains. So let's say that we're generating it for ZC104 board. We can do it for any board, like most of these boards are quite similar in nature. So this thing here actually refers to the soft link, like what it is referring to. So it's a symbolic link and it's opening that particular file. So by this command like ls-ltr, you can see that which file it is actually referring to, and you can just like you can see which file it is, the soft link is referring to. So you don't have to write the code again and again. If certain files are saying, you can just create a soft link to that file. So in this case it has created a soft link to pink Z2 board, and in this case you can see that it is not pointing to anything else in Z2's case. So we can generate it for Z2, and like most of these things will remain similar for the other boards as well. So we just want to get an experience at how we use Vitis HLS and all these things together. So now in the readme file you can see that this folder helps users rebuild the Vitis library IP for Vivado HLS flow. The Vitis lib folder is git submodule pointing to the Vitis libraries. So this Vitis lib folder is like a submodule pointing to the Vitis libraries. So quickly, if we look at the Vitis libraries where all it is present, so you can do that from the boards itself, like ping Z2. So sorry, not ping Z2, actually the IP, the general IP which it is creating, and here it is pointing to, let me open it in a new tab. Once again. So this is where it is pointing to this particular commit number to this particular branch. If obviously we open the latest Vitis library folder, it would look something like this, and it's quite an updated library, like they keep on putting newer and newer things. At the same time, want to show you the Vitis libraries folder. So these are Vitis accelerated libraries, and multiple of them are there for you to actually utilize, like the BLAS library for all the common linear algebra operations using the algorithms for doing the optimized BLAS routine. Similar to this is the CUDA BLAS library. So all these things are actually like having one-to-one correspondence. So you can most of the things which you see there you will find somehow or the other, you'll find it here as well in NVIDIA, whatever it is that you see in different companies, they will have similar implementations like NVIDIA CU BLAS library, the fast Fourier transform library, CU solver, CU sparse, something for random number. So what you are seeing here, and like blockchain solutions, database libraries, graph libraries. So these are like high level written C code, and it will automatically get mapped to your IPs. Like it will create the IP for you in the HLS once you use these libraries in your HLS code. So it's a good technique to actually build upon these libraries, and in this particular lab we'll be building upon the Vitis Vision library. We'll see in a minute what we're about to do. So the Vision library includes applications it's vision processing from edge to cloud, and it has adaptable throughput requirements while being power efficient. So they have mentioned many things about the library. So typically, like if there is multi-streams coming from the different cameras, so CPU does the pre-processing for each thing, and then the GPU does the AI inferencing, and then again CPU does the decision making and shows it. So it's taking almost 13.5 milliseconds. But with the adaptive platform like which we have, the FPGA, the pre-processing, AI inferencing, decision making all happens in one single chip and in one single memory space, and therefore it gives so much better latency. So no matter where your FPGA is deployed, you can reconfigure it in the field. So Vitis Vision library enables you to develop and deploy accelerated computer vision and image processing applications on these platforms while continue to work at a high level abstraction. So in one video maybe I'll walk you through the different things which they are telling, that how the bilateral filter, the canny edge detection, color thresholding, dense periodical optical flow, fast corner detection. Like they have benchmarked the FPS on the PL, and Vitis Vision library kernels, the AI FPS performance you can see. And it shows that how the design methodology works, that you have a software hardware developer, and then in the Vitis IDE you write the C++ code. There are certain user defined libraries, so you create HLS kernel, high level synthesis kernel wrappers for certain user defined libraries and certain Vitis libraries, and then make file driven compilation for HLS compiler, and then you evaluate the script by doing the hardware emulation or doing the Xilinx runtime library, and finally execute it on the hardware. And this is what we'll do. Faster than these like vision libraries and everything is the Vitis Vision AI engine design methodology, and AI engines actually convert something to what they call as data flow graphs, and here you create HLS kernel wrappers, here you construct data flow graphs. So it's like a similar methodology, but it provides even higher acceleration for your application. So what am I going to do is that I'll download the zip format of these files. So we'll wait for it to download. Either we can fully copy this whole thing, or because every time if you're cloning this repository, so it is downloading all the previous commits and versions that how this repository has moved. So rather than doing it this way, what we can do is a smarter move in which we can go to this particular repository where we are wanting to go. Inside the pink hello world example, inside the boards, inside app IP, and where the Vitis library is there. So here we can actually open in terminal. Here we can do git clone this repository, but before we actually clone this repository, we just want the depth to be 1, which means the latest commit on this repository, and the branch, so many branches will be there that, like, we don't want to unnecessarily clone all the branches, so we'll just clone the main branch. So it will clone all the Vitis libraries which are there, and this thing will be much quicker. So we have cloned all this repository and it has come here. Now what you can do is basically want the vision library and certain utility libraries, because that's what we're functioning. But for completeness sake, let's just copy all these. Let's cut from here, or let's copy from here itself and paste this. So you can just change the name of that file as well. So inside each of these files, if you go, what you will observe is that it's a very similar inside hardware, so there are certain images for you to test on, and for each, so this is the data actually, extension L1, L2, L3. Sorry, you went to the wrong folder. We have to go to the include folder. So in the include folder, you will see the different, like I told you about the AI things. There are certain common functionalities. So all the HPP files are written here, and the core files, the DNN files, and they all have a similar structure like XF underscore fast. Certain image processing things are there, and the video files. So this is what, and in the examples folder, you can, inside the L1 examples folder, you can see the different sort of examples which you can directly use, like in range, intergrambling, is pipeline, quantization, tethering, PyDrown phase. So all these things are paint masks. So these are like standard vision things which are available for you to actually use in your projects. For now, we'll just actually in the VS Code where we had opened this. So we have for everything. So now in the Vitis library, you have this all these files available with you. So for executing, if we read the main file, in the libraries folders, once we have all the Vitis libraries installed here, you can just click on make, and what this make command will do is actually execute this make file. So it's a very standard way of doing things in this hardware software codesign. Like even in the industry, actually, we always, like in any company which you go, you always use make files to rebuild things and work. So here the IP which we're going to build is resize. So this we're just calling it the IP, the variable IP in the make file. And in the Vitis library include, we're executing this command. So actually anything inside $ will execute just like that. So in the shell script, it will execute read link. So it will read the link to this pink hello world board's IP, Vitis lib vision L1 include. So this we had just now seen that in Vitis lib vision L1 include. So all these things which are there right now, all of them will get imported while we're while we're compiling the C code, and then as soon as it comes, so since we're just typing make, so it will run make all, and inside all, before it will run HLS. Once it comes inside HLS, before echoing this, it will actually execute this command. Here it will execute Vitis HLS -f build.tickle script. So the build.tickle script which you are seeing, which is this build.tickle script, it will set all these things. Like it will open a project called resize, set top to resize accelerator. It will add certain source files. So the source files which it will add are two files called xf resize excel stream.cpp file, and it will have certain C flags associated with it, and it will include the Vitis library include folder, which is get passed along with this command the second argument of it. So basically it's a huge C code. Not all of it is useful in one go, but this is the C++ file which is actually like, helping you build that resizer thing, whatever thing you have envisioned. So now it's like we'll just look at this command once, look at this code once. So resize exciter stream. So we use a custom access 2x fmat, and so let's like this code is now the commented version of this for you to help for you to follow along. So let's look at this. I'll just zoom into this a little bit and let me maximize this. So firstly, all these include statements you're seeing are the different libraries which we need for this HLS design to work. The HLS stream is required for handling streams in high level synthesis, and this header file we're including for building that. Then from the common, we're including the xf common.hpp file. So I had shown you this file that in the Vitis library in the common folder, in this common folder. So all these files we're actually using, and particularly we're using xf common.hpp, this file. So I'll open it right here. So this file is further including the structs, params and the types. So the structs, so it's just the header files which we're importing here. The actual implementation is mentioned somewhere else. So these are the files which you don't have to actually again and again write. You can directly utilize these sorts of files, and they are written in a template kind of a format in C++, which looks complicated to write, but if you start understanding, it's not that difficult. So let's, before I just wanted to show you that how these files are getting included inside this folder. And then from the image processing, you pick up the xf resize.hpp file. So from image processing, you pick up the file which is called xf_resize. So this file you pick up, and this obviously includes the resize headers.h file, and that's how the C code is actually structured, that you keep on including and you write the code in a very modular way with different files, which all files to use in order to compile a project. And that's how the source rows, source columns, destination columns, all these things are actually like the interpolation type which we have chosen. I'll now again show you once the pink hello world notebook edge. So here whatever things we are using, like the bilinear interpolation, particularly related to the IP. So basically we're creating this whole design, we're creating this IP, resize IP along with this DMA connection, and because it works on 24 bits, so that's what we're trying to do here. I had explained to you that particularly this part, the register offset, where we are storing the source rows, source columns, destination columns, and how the IP setting writing 0 cross 81 to this register, it will start the whole process. So all these things are actually mentioned inside this C code, how we're managing things, how we're creating this IP, and it is using constructs, the resize function from this. So you don't have to actually build everything from scratch. You can just be very smart enough to leverage upon the codes written by others. Obviously this requires you to understand and explore the different things which they are offering and how each of them work. So each pixel has 24 bits, 8 bits per channel, and the number of pixels processed per clock cycle. Set the dimensions of the image, like whatever dimensions you want to set for ultra HD resolution. You have to set the filter size, the type of image, and interpolation method for resizing. So this interpolation method which we're choosing, xf_ interpolation. So this you can see that if I do Control F here, so you can check the interpolation type, like based on that interpolation type, this code will run in the background. Then define a custom data type for handling EXI streams. So Xilinx standard data exchange protocol, in fact any company's standard data exchange protocol is EXI only. So you define this function for handling the data width and the HLS stream type to be used. Then we use custom functions EXI to XFMAT and XFMAT to EXI stream functions instead of the default functions, because the hello world example uses a regular DMA. So instead of using these two functions like which are standard defined, we are defining two custom functions, and because our use case is much simpler, and assert the last signal only for the final pixel of the image as needed. So the function to convert an EXI stream to this XF CV mat format for image processing is that you create a template of width, type, rows, columns, and in PPC. And here you have written the function where you declare an EXI stream interface. You calculate the pixel width which is coming. You get the number of rows and columns from the image matrix. You ensure that the dimensions of the image do not exceed the matrix limits, and you read the EXI stream and convert it to the corresponding format. Prevent loop flattening to maintain pipeline structure. So loop flattening, so there are certain pragmas defined in HLS to help guide the architecture, what RTL design it will generate and how many resources it will use, and pipeline with an initial interval of 1 clock cycle. So all these things you are defining which are related to HLS. You read data from the EXI stream which is coming and write pixel data into the image matrix. There is a function to convert again the matrix back to the EXI stream, because what you have to send according to this diagram which we had seen, that from the DMN, the data width converter, this function which we have written. So this resize IP we are picking directly from the from this resize function, and this part where we are converting data width converter back to the DMA is 32-bit. So the 32-bit EXI stream protocol. So again that is the function which this thing is doing. Read the XF CV mat and convert it to an EXI stream thing, and finally this is the main function to resize the image using the XF OpenCV resize function. This function takes input and output streams and the dimensions of the source and destination images. So the dimensions like are being passed here, and this input stream and the output stream is like being presented to you. So this is the input source stream and this is the destination stream it will write to. Here we are creating two ports on the IP. Like this is how you actually create a port. The hashtag pragma is for guiding the HLS, hashtag pragma HLS. Then we are creating an interface of type EXI stream register, both port equal to source. So declare source as an EXI stream interface, similar for destination. There are certain control interfaces for HLS accelerator which we are making, like over the EXI light port we are having the source rows, source columns, destination columns. So at this point a return signal for the EXI light interface, and we declare the image matrices for the source and destination images based on the source rows and columns and the destination rows and columns. So this is for the matrix like image processing, matrix multiplication, matrix manipulation, and we enable the data flow optimization for concurrent execution. We perform the resize operation. So firstly we'll convert the input EXI stream to the XF CV mat object for processing, and here we'll call this function, we'll pass this data width, type, height, width, and then PIX with source and source matrix, the stream and the matrix basically. Then we'll perform the resize operation using the XF OpenCV's resize function. So simply we're calling here the XFCV resize function which is mentioned here, and it will take in input as the interpolation technique, the type, height, width, and then PX and max down scale. You passing the source matrix and the destination matrix which we have created, and this will fill in the destination matrix, and then we'll convert the processed thing back to an EXI stream and pass it. So I hope this code is clear to you. So now with this clarity, let's run the make command and see if this thing is causing any errors. So it has started the Vitis HLS flow, and it has taken the source, the tickle script through which it will run the entire thing, the build.tickle file. So there was a small mistake where instead of type def xf : cv, we have to use just the global namespace. This was what the error was saying. And now you can see, like, I'll just quickly walk you through these log files. In fact, let it all get completed. So I've copied the entire thing here, and let's quickly review that what all has happened when we have run this make file. So this is the command which we execute, the make file, and internally it executed this command. So the build.tickle script is the set of console level scripts, like, which help the Vivado or the Vitis or any Vitis HLS software to execute certain commands. And we have already seen this build.tickle script, that what it is doing, that it's opening a project called resize, set top, resize axle, it is adding these files, and then it's setting the part with zinc, it's creating clock periods, setting clock uncertainty, and then from its synthesizing and export IP using Vivado flow. So C synthesis design, and it's configuring some export, C synthesis design, and then export design. It's calling it the image resizing IP, and this all we'll see. In fact, better, like, since we have already this Vivado open with us, I'll just click on like project, open project, and in the documents folder, in our pink hello world, boards, IP, resize,